This is the video presentation of the work entitled Low-Cost Wireless Testbed for Internet of Things Ad Hoc Networks Prototyping and Evaluation. This work was accepted for poster presentation in the IEEE World Forum on Internet of Things 2020, adapted due to the COVID-19 pandemic. When new networking protocols are developed, researchers rely on simulation platforms in order to validate their work. Network simulators provide a valuable framework to enable this type of research. Some simulators used by the community and their corresponding features can be seen in the following table. To advance and deploy networking protocols in real-world applications, researchers face the challenging task of porting the protocols from a simulation to an actual software implementation, which may involve low-level programming and hardware and kernel interface, or driver development to interface with the hardware components. This work attempts to bridge the gap between simulation and testbed evaluation of wireless ad hoc networks. It uses low-cost, off-the-shelf components and open-source software to enable research-aware protocols to be tested in real devices. In this work, we opted to use the Raspberry Pi 3 Model B as the logic board of our nodes. It is a low-cost and highly customizable computer. Each logic board is attached to a power supply through the current sensor. We use the IEEE 219 in order to obtain accurate measurements of the current that the logic board drains. The power supply used in each node are 4 common AA batteries that provide the voltage required by the logic board. The picture below in the slide show what the exact wiring of each node is. We opted to use the NS3 network simulator as the protocol development framework due to its open-source license and hardware integration. It provides direct access to the network interface through its FD net device and real-time simulator libraries. The hardware must be able to work in ad hoc mode in order to enable NS3 to inject frames into the network card. We developed the necessary library to provide sensor readings to the simulation framework. The library model implements a simple field gauge model in which the current reading is used to estimate the drained energy from the power supply at a fixed time interval. We call it the IEEE 219 source. As mentioned, the hardware must be able to work in ad hoc mode. And the logic board must also provide I2C interface in order to connect the current sensor. We used the Raspbian operating system, a Linux distribution developed by the Raspberry Pi Foundation. At the time of development, the kernel version of the OS was 4.14.50. We evaluate the network performance on a network with 5 nodes, each node comprised of the same hardware as previously described. First, we place the nodes in a straight line topology. Given the indoor characteristic we are able to control the topology as seen in the picture below. The results from this indoor experiment are then used as benchmark to compare with other experiments. We use the results from a one-hop communication as the best case scenario between the server node, the triangle seen in the picture, and the first node that it is connected to. And then we use a four-hop communication as the worst case scenario, as seen in the picture. We compare the indoor experiments with an outdoor setup, in which we do not have control over the topology of the network. We use the outdoor experiment to show the feasibility of the system proposed in this paper. The experiments are executed during non-business hours to avoid human interference. The nodes were placed apart in an open field area known as the Quad, on the campus of the University of Nevada, Reno. For each experiment setup, we compare different routing protocols: AODV, DSDV, OLSR, OLSR with expected transmission count as the link metric, and split path routing. Split path is an energy-aware routing protocol proposed in a previous work of our research group. Initial results show an expected behavior where the one-hop scenario outperforms the others. And because there are only two nodes in that scenario, the energy consumption is also proportional to the link throughput. The network throughput achieved in the testbed is quite low if compared to other common wireless networks. One of the reasons is later discussed in the conclusion of this presentation. We also compared the energy model provided by the NS3 simulator framework with a similar model, but with actual current readings from our INA 219 sensor. We can see that both simulation and experiment follow a similar trend. However, we can also observe that the simulation model needs to be accurately adjusted if it wants to reflect a real network scenario. This adjustment is not trivial because it depends on the actual service running on each node of the network. More computationally intensive processes will require more energy, and vice versa. In this work, we propose a low-cost testbed system that reduces the time needed to convert a protocol implemented in a simulator into real-world networked devices by enabling code reuse. The testbed can provide values closer to reality, reducing the need for hard assumptions in terms of energy-aware protocols. However, the system has its limitations. It is limited since it only allows a single packet input and output at a time from the network interface card. In the future, it could bypass the kernel and provide direct access to the network interface card buffer to the user space, where the simulation actually runs, by using the NetMap device instead of the FD net device, which is currently being developed by the NS3 community. If you have any questions, you can forward your inquiries to the following address.